Welcome to our Karl Fischer Titration Guide, your complete walkthrough to mastering moisture analysis in the lab, step by step. Contents. Here's what we'll cover today. The core principle, the reagents and setup, calibration, real-world applications, performance control, and finally, the advantages and comparison with other techniques. Think of this as your complete guide to becoming confident in Karl Fischer Titration. By the end, you'll understand both the science and the best practices behind it. Let's start with the foundation, the core principle. Core principle. This is where it all begins. Understanding what Karl Fischer Titration truly measures and why it's so reliable. What Karl Fischer Titration measures? Karl Fischer Titration quantifies water directly by reacting it with iodine, sulfur dioxide, and a base. Developed in 1935, it's still the gold standard for moisture analysis because it measures only water, not other volatile compounds. Unlike Lawson drying methods, it gives precise, chemical proof of water content. So when accuracy matters, this is the method laboratories trust most. Chemistry behind the reaction. Now, let's peek at the reaction itself. It only happens when water is present. Iodine acts as the oxidizer, sulfur dioxide forms an intermediate, and a base keeps the system stable for a sharp endpoint. The reaction converts iodine and water into hydrogen iodide and sulfur trioxide. This clear, predictable chemistry is what makes the method so dependable. Reagents and setup. Alright, now that we know the chemistry, let's look at the ingredients and setup that make it all work. Modern KF reagent composition. Standard reagents usually include methanol, iodine, sulfur dioxide, and an imidazole base. For special cases like aldehydes and ketones, we use methanol-free solvents to prevent side reactions. And just as important, everything is kept in airtight vessels to keep humidity out. One small leak can throw off the whole measurement. Volumetric versus coulometric paths. There are two main paths in Karl Fischer titration, volumetric and coulometric. The volumetric method adds iodine from a burette, great for larger water content between 0.1 to 100 milligrams. The coulometric method generates iodine electrochemically, perfect for ultra-low moisture in the microgram range. Choosing the right one depends on how much water you expect to find. Calibration. Next up is calibration, the heart of accuracy in any titration method. Titer determination. To ensure your results are trustworthy, you must determine the titer, which tells you how much water reacts per milliliter of reagent. We use sodium tartrate dihydrate, which contains exactly 15.66% water, as a reference. The formula links the sample's weight to the reagent volume used, giving precise traceability. This simple step keeps your instrument aligned and reliable. Routine verification protocol. Daily verification is just as important as the initial calibration. You'll check the titer each day using disodium tartrate and ensure it's within plus or minus 1%. If drift appears, re-standardize right away to avoid cumulative errors. These habits keep your results rock solid, especially in pharmaceutical and petrochemical labs. Applications. Now that we've got the setup right, let's explore where Karl Fischer titration truly shines in real-world industries. Industry-specific sample handling. In pharmaceuticals, it ensures drug stability by checking solvent purity. In oils and fats, we use special solvents to handle biofuel samples. For gases, we use evaporators for consistent measurement, and for plastics, oven extraction at 105 to 200 degrees Celsius works best. Each approach tailors the process to the material's unique properties. Scope across physical states. Karl Fischer titration isn't limited to one type of material. It handles solids, liquids, and gases. Solids can be tested directly or via an oven. Liquids are injected into the cell, and gases are bubbled through it. This versatility is why industries from cosmetics to biofuels rely on it daily. It's a universal moisture analysis tool with unmatched adaptability. Performance control. Accuracy doesn't happen by chance. It requires control over several critical parameters. Critical parameters for accuracy. The ideal pH range is between 5 and 7.5. Below pH 2, the reaction stalls. Above pH 8, side reactions appear. Keeping humidity low, solvents fresh, and systems airtight ensures consistent results. Control these, and you'll master repeatable, bias-free titrations every time. Recognizing method limits. Of course, every method has its limits. Karl Fischer titration consumes the sample, so it's not reusable, and reagent consumption is continuous. Coulometric titration can be slow for high-water samples, while volumetric lacks sensitivity for very dry materials. Plus, certain reactive compounds and nonpolar matrices can interfere, so understanding these limits helps you choose wisely. Advantages and comparison. Now, let's see how Karl Fischer titration stacks up against other moisture determination methods. KF versus loss-on drying and gravimetric. Karl Fischer titration focuses solely on water, giving high precision and fast results with small samples. Meanwhile, loss-on drying and gravimetric methods can include other volatiles, leading to lower accuracy and longer analysis times. KF is also pharmacopoeia approved, making it the preferred method for regulated industries. Simply put, it's specific, fast, and dependable. Key takeaways for reliable moisture data. Here's how to keep your results flawless. Choose the right mode for your sample, calibrate daily with certified standards, control environmental factors, and validate your method per sample type. These steps make sure every data point you generate is scientifically defensible. That's why Karl Fischer remains the benchmark for moisture testing. Thank you. And that wraps up our deep dive into Karl Fischer titration. I hope this helped you understand not just the science, but the practical know-how behind accurate moisture analysis. Thanks for joining me.